and share my screen. Okay, so I screwed up a little bit last week. I missed a couple of pages from the components section. So we're going to talk about some components first before we get into the circuits. And the first topic is actually it's integrated circuits, but they have a couple of questions here about analog integrated circuits. And the first one is about op amps. So the op amp is a type of integrated circuit, and the package on the left is an 8-pin dual inline package or 8-pin dip package, and that's what a lot of op amps come in. And that's that kind of package. Sometimes you see them in an 8-pin package, and those may have 2 op amps in them in a single package. This on the right is a sort of a typical op amp circuit. And this is a simple amplifier circuit. And the nice thing about op amps, is if you're using them as like an audio op amp or whatever, is that the gain of the op amp is simply R1 over R2. So with a couple 3 resistors, you hit in an op amp circuit, op amp IC, you have a really nice gain amp, high gain amplifier. And the reason they can get away with that is that the way the op amp is designed inside, without those resistors, they have almost infinite gain. They have a very high gain, and then by putting these resistors on, you limit it. You can also use op amps to do other functions, not just simple linear amplification. And as a simple example here, if you, and it all has to do with frequency response, right? You know, last week we talked about capacitors, the reactance of a capacitor going up as the frequency increases, or going down as the frequency increases, and the reactance of an inductor going up as the frequency increases. Well, if you put some components in here, you actually get like a bandpass filter instead of just a regular amplifier. And so here the gain is R1 over R2. Well, it's sort of what you do then is you figure out what the impedance is of this and the impedance of that, and it's the impedance of, this circuit over the impedance of that circuit. And if you go through all the calculations, which again, this took like a week in engineering school. You'll find out it's a bandpass filter, and you can go online. And in fact, that's what I did to make sure I got this schematic right. You can go online and look up these circuits, and you can play with them yourself. You could, if you had a bunch of capacitors and resistors, you could, in an op amp, you could play with these yourself. One way we used to use op amps a lot before we had a lot of digital signal processing, was for bandpass filters for receivers. So, and we talked about in the tech class what the width of a filter should be for different modes, right? And just had to let somebody else in here. We talked about the bandwidth for different modes. Well, you can tailor these circuits to give you a wide band pass, like say for sideband, or a narrow band pass for CW. And it's all with playing with these resistors and capacitors. So these are very cool circuits. Question: what kind of device is an integrated circuit operational amplifier? Answer: analog. So that's that. Next question is about a circuit called the monolithic microwave integrated circuit. In some ways, you can think of this as a micro. The thing about most op amps is they don't have a high frequency response. You know, usually they're good at frequencies up to a megahertz or so. Although lately some op amps have been increasing the bandwidth of op amps. It's kind of amazing what they're doing with integrated circuits these days in especially analog integrated circuits. But these you can think of these monolithic microwave ICs as sort of microwave op amps in a way. You know, so this is the package here, and this is the circuit diagram, and you see it's very similar to what the op amp was. And so it's just that these things are made to operate at microwave frequencies where the other ones really weren't. You know, this package would mount on a surface mount board, and why is that? Is that to keep these lead lengths as short as possible so that it will operate in the microwave range. So, question, what is meant by the term MMIC? Answer, monolithic microwave integrated circuit. So this next section here is well, I take that back. Let's talk about well, this next section does start talking about digital integrated circuits, and this is always the hardest section to cover, because, you know, it's getting back to engineering school. You know, there was a whole semester on digital logic, right? And I got about 10 minutes here to talk about that. But there's several different kinds of digital logic. And, you know, a common one is called TTL, or transistor logic. The other most common is CMOS. It stands for complementary metal oxide semiconductor. And we talked a little bit about a MOSFET last week, if you remember. And I showed you the internal structure of an MOS transistor. Well, this is an IC made with all those transistors. There's, you know, thousands of transistors in this IC. And this is a type of IC called a read-only memory. So typically a manufacturer would program the data in this IC by putting a special mask on it. And the mask would have different data for different customers. But in any case, it's read-only. So that's read-only memory, ROM. We don't really use these, and this is where the question pool really hasn't kept up with technology too much, but we really don't use read-only memories a whole lot anymore. And the reason for that is, again, it's advances in IC technology. Nowadays, we mostly use flash memory. And the nice thing about flash memory is that it sort of can act like read-only memory, but it's more easily programmable. So, you know, if you think about it, if somebody made a mistake in this chip, right, and this contains 4 million bits. Well, if somebody made, you know, a mistake in 2 or 3 of those bits, then the whole chip you just throw it out because it's no good anymore. So that's why we use flash nowadays, because they've been able to make flash almost as dense as this kind of read-only memory. So a couple of questions about this. Question, which of the following is an advantage of CMOS integrated circuits compared to TTL integrated circuits? Well, the big advantage is that CMOS has lower power. And you know, there's a lot of reasons for that, and I could draw circuits, but just all you got to do is really remember it's lower power. And that's why, like, you know, most microprocessors and such these days use some kind of MOS transistors. Question, what is meant by the term ROM? Answer, read-only memory. And that's the nice thing about it, a read-only memory, is that the data never goes away. You know, if you had regular memory chips, like when you turn on your computer, right? You turn it off, whatever you had in memory is now gone. Well, with a read-only memory, and also with flash memory too, a lot of times, the data doesn't go away. It stays there. So when you turn the power back on, the data is still there. So question, and in either case, those kind of memories would be called non-volatile, meaning that they're not going to change. So question, what is meant when memory is characterized as non-volatile? Answer, the stored information is maintained even if power is removed. So that's read-only memories, CMOS and TTO. Any questions? Okay. So continuing on with the component aspect of this, we'll talk a little bit about displays. And the most common type of displays we use these days are either LCD displays like this one or LED displays. And the nice thing about LED displays is that they're a little bit brighter, and you can actually see that here, right? So if you had an application where you wanted that display to be seen across the room or something, you might use an LED display. If you're talking about something on a device like an amateur radio, piece of amateur radio equipment, you might use an LCD display because you can get they can be denser. The pixels are denser, and it'll still be visible, but you can get a lot more on there. So in an LED display, what do you have? Well, you got to actually have, you have diodes, right? And each of these segments, well, it's not really. Each of these segments here is a separate diode. So this one number here consists of 7 different diodes. And how does a diode turn on? Well, if you forward bias it, if you put make this lead, the cathode, more or the anode more positive than the voltage on the cathode. That's the question. How is an LED biased when emitting light? Answer, forward biased. Call that forward biased. Question, which of the following is a characteristic of a liquid crystal display? Answer, it utilizes ambient or backlighting. So this operates a little differently. These things don't emit any light at all. Instead, what happens is when you put a voltage across one of these pixels here, it becomes opaque. And so then to actually be able to see the display, you either have to be in a place where there's ample ambient lighting, or it uses a backlighting. So in this display, there's probably a backlight on there. And another one advantage of the LCD is another advantage of the LCD display uses less power, because here you're actually putting probably a fair amount of current in there to get the light to light up. But here you're just putting a voltage on a bit of liquid crystal, and it's turning opaque. So it doesn't consume as much power. Any questions about displays? All right. Talk a little bit about connectors. So here's a bunch of connectors that we use commonly in amateur radio. The phono, jack, and plug; those are fairly common. There's an interesting history about the phono plug. Sometimes they call it the RCA jack, right? I don't know if you ever heard that. And why is that? Because it was developed by the Radio Corporation of America in like the 1940s, when RCA produced radios with phonographs in them. And the shortwave radio I was talking about that I sat in front of as a kid, I actually have it downstairs still. I've carted it with me all these years, but it has a pull-out phonograph too. Mine's a Philco, so it didn't have an RCA plug in it. But the RCA units, they use this jack and plug to connect the phonograph to the radio, to the amplifier in the radio. And so that's why they called it an RCA jack or a phono jack, because that's it. And we've been using it for 80 years now, like almost 80 years. So that's kind of amazing to me. But that just goes to show how useful the design was. And we still use these for audio a lot. The next three are all RF connectors. The PL259, that's the most commonly used RF connector to connect antennas to radios. The N connector is getting to be more popular, and the reason for that is it's really a better connector. It can be waterproofed, and it can be it presents a much more controlled impedance to a signal than does the PL259. And then the SMA connector is becoming kind of popular because all these small handheld radios use some type of SMA connector because they're so small, and the SMA connectors are small, physically small, so they can go on these radios. So some questions about this. Which of these connector types is commonly used for audio signals in an amateur radio station? Answer, RCA phono. Question, which of these connector types is commonly used for RF connections at frequencies up to 150 megahertz? Answer, PL259. And really 150 megahertz is about the highest you want to go with a PL259. Although, on a lot of 2-meter 440 radios, the PL259 is the only connector on there, but it's really not optimum for the 70 centimeter band. Question, which of the following describes an N-type connector or a type N connector? Answer, a moisture-resistant RF connector useful to 10 gigahertz. So that's pretty high frequency. And what is a type SMA connector? A small threaded connector suitable for signals up to several gigahertz. All right, any questions about connectors?
Yes.
Sure.
Using the N connector, what is the advantage about besides being waterproof? Why is it better for high frequency?
Well, so you see, wrong side. You see what in the PL259, you're relying on the shell to provide the return connection. And right away, you see that the diameter of the shell is different than the diameter of the body. Mm-hmm. And at HF, that's not a big deal. But once you get higher up in frequency, that does present it does present a mismatch. In the N connector, so you have the center pin, and then this is sort of like the outer shell. That's the return connection, and then you have a separate shell. So you're not relying on the shell to present for the impedance. For impedance.
Could you use the N connector for the lower frequencies?
Excuse me?
So can you use the N connector for the lower?
Oh yeah, absolutely. That's why I really wish that amateur radio manufacturers would put N connectors even on their HF radios, because it's just a better connector. And yeah, it costs a little bit more, but you know, you're spending $1,000 on a radio. Yeah, get an end connector on it. Get a good connector on it.
Thank you.
Yeah.
And what do you mean by the return?
Well, so this thing connects to coaxial cable, right? And you got a center conductor, and then I should have said the shield. You got a shield in the coax connector. The shield will connect to this part here and the shell here. See what I'm saying? I should have a picture maybe of a cable, but the cable will stick out the back here. And like I said, there's a center conductor, and then the shield goes around it. And this part connects to the shield. And keeping that spacing between the center conductor and the shield is what preserves the characteristic impedance of the transmission line. So when you got a difference as you have here with the PL259, you actually have what they sometimes call it an impedance bump or whatever. And that impedance bump will actually contribute to a higher SWR. But on HF, it's not that big a deal. But when you get up in the higher frequencies, it does become an issue.
So the shell kind of loses some of the shielding. Is that what I'm to assume?
I wouldn't say it quite that way. Here, think about it this way. So here's the coax, right? And here's the connector. This center conductor goes through to the pin, and the characteristic impedance. The characteristic impedance of the line is dependent on not only the dimensions here, the physical dimensions, but the type of dielectric here, and that all changes once you get into a PL259, because now this distance, B is greater than A. So the impedance is actually going to be different in that connector. And that'll contribute to a higher SWR. Does that make sense? All right.
It does make
Any
sense.
other questions? Okay. I think the reason that, talking about like the RCA photo jack being around since the 40s, the PL259 has been around since World War II too. And I mean, it's just one of those things that we just continue to use it because that's what we've always used, Even a BNC connector, I should have put a BNC. BNC connectors look more like this. Even a BNC connector would be better to use for ham radio purposes. But the problem with the BNC connector is it's not good at higher power. I forget what kind of power you can put through a BNC connector. But you can put a kilowatt through this thing, but a BNC you can't. And this will also handle high power too. All right. So now we'll talk about some practical circuits. And the first thing we'll talk about is the half-wave rectifier, actually, and all kinds of rectifiers, but the first thing I have is a half-wave rectifier. So I remember we said that the diode, the diode allows current to flow in only one direction. And so we can use the diode to quote unquote rectify AC, that is turn AC to DC. So if I input an AC signal into this transformer, I'll get some kind of voltage on the secondary, and this diode will only allow current to flow during the positive portion of the AC cycle. So this is what I'm inputting. This is what I'm outputting. I'm only outputting anything during the positive portions of the cycle. This is called a half-wave rectifier because it's rectifying half of the cycle. Should really be called a half-cycle rectifier, I guess. But we call it a half-wave rectifier. And there are some power supplies that are made using this kind of rectifier, but it's wasting the power in this portion of the AC cycle. So that's kind of not a good thing. So to get around that, or to improve on that, I should say, we use full wave rectifiers. There's two types of full wave rectifiers. This is one using two diodes, and this one is sometimes called the bridge rectifier. Now, what's the difference? Well, besides being 4 diodes versus 2 diodes, the biggest thing is the 2 diode full wave rectifier requires the full output voltage. How should I say this? It requires twice the windings in the secondary because it needs this center tap, because it needs this number of windings on both halves of the cycle. Whereas the bridge rectifier only needs one set of windings because of the way the circuit steers the current. So what does the output of this look like? So you get, so if this was the input, this is the output. And so it turns this negative half of the cycle into a positive going DC pulse. This is great. This is great because not only do we get more power, we get the full power of the AC input, but we actually get less ripple here. Because eventually we want to turn this into a steady DC voltage, right? So the bridge rectifier works out a lot better because transformers are expensive, and to have more windings here would makes that transformer just more expensive. So we have the higher expense for the diodes here, but the higher, nowadays anyway, the higher expense for the transformer sort of swamps out the whatever advantage you get from having only 2 diodes. So nowadays, if you look at mostly any linear, these are used in linear power supplies, right? If you look at any linear power supply, you'll find a bridge rectifier in there rather than a half wave rectifier or the other type of full wave rectifier. So questions. What portion of the AC cycle is converted to DC by a half wave rectifier? Answer 180 degrees. So if you think of a whole cycle as being 360 degrees and you're only getting half of it, well, that's 180 degrees. Question, what portion of the AC cycle is converted to DC by a full wave rectifier? Answer 360 degrees. Question, what is an advantage of a half-wave rectifier in a power supply? Answer, only 1 diode is required. Question, which type of rectifier circuit uses 2 diodes and a center tap transformer? Answer, full wave. Why they don't ask any questions about bridge rectifiers, I don't know, because like I say, they're much more popular these days. In fact, you can get packages with 4 diodes in it, and it's just got the 4 connections on it, Question, what is the output waveform of an unfiltered full wave rectifier connected to a resistive load, which is what we got here, right? Answer, a series of DC pulses at twice the frequency of the AC input, right? So this was one cycle, but here one cycle is half that, so you've got twice the frequency. Any questions about rectifiers? Sometimes
So
these are actually called rectifier diodes.
Can you review that last statement, Dan, that you just made
Which one?
about the frequency?
Oh, okay. So if this was the input, right? And say it was 120 cycles per second, right? I mean 60 hertz cycles per second. That's what you get out of the wall socket. If you sort of superimpose that on here, right, you'd see something like this, right? So that's one cycle. Here, one cycle is half that. So the frequency of the output is 2 times the frequency of the input.
So the test just refers to the full wave rectifier only as the top one, the one that's center tapped. It doesn't talk about bridge ones.
No, there's no question about that, but I wanted to include it because that's what we use mostly in ham radio. You know, like I use an Astron linear power supply in my station. It's got a bridge rectifier in it.
Is the top one just referred to as a center tapped one, or does it have a name like bridge?
The transformer is center tapped, but this is still just called a full wave rectifier.
Okay, they're both.
This is full. Okay. This is a full wave. This is a bridge rectifier, and that's when you say bridge, you sort of assume full wave.
Great.
You know, I guess that's a way to think about it.
And so I'm guessing that if you use a full wave rectifier, you have to use a filter, right? Because it's going to be twice the frequency of the AC signal, correct?
You have to use what now?
Filter.
Oh yeah. In fact, that's the next section here.
Okay, and then if you use a half wave amplifier, you don't have to use a filter because it's going to maintain the frequency.
Oh no! You still have to. In fact, you have to use more filtering if you use the half wave rectifier. I mean, because what you want to get out of it is a DC voltage, right? So you'd have to use even more filtering.
I got you. Okay.
Trying to smooth those bumps out. You want those bumps to be all just a smooth line going across.
Right. So if this was say this was that's the DC voltage you want right there, you know. And how do you do that? Well, get rid of the resistor. You put some capacitors in here. You might put an inductor in here. Yeah, you might have something like that. And in actuality, even instead of this inductor, you want to have a voltage regulator IC that'll actually even do a better job of regulating the output voltage. You know, in some cases you might be able to get away with this, but you know, voltage regulators are so cheap, you might as well use one, right? I mean, that's sort of just the way it is. So the question, which of the following components are used in a power supply filter network? Answer, capacitors and inductors. And then if it's if you know you're supplying a lot of current here and these are big capacitors, you might want to put a high value of resistor on the output here. You know, 1 megohm or something. Why is that? Well, that's when you turn the power off, the current will then go through the resistor, you know, the power off to the the whatever load you've got out here, the radio, or whatever. When you turn the radio off, no current's going to flow out here, right? These capacitors would be charged up. And if you had a big resistor here, it would have little effect on the output voltage, but then would discharge these capacitors. And that's why you do that. Sometimes this is called a bleeder resistor. So question, what useful feature does a power supply bleeder resistor provide? Answer, it ensures that the filter capacitors are discharged when power is removed. And why do you want that? Well, if you're doing some work on your station, rearranging things, I don't know what, whatever you're doing, if you turn that power supply off and then start moving things around, well, you don't want to get any metal like a screwdriver or something across the plus and minus if there's still a lot of voltage out here. So that bleeder resistor will discharge that current right away, and the voltage will drop to zero. I even go a step further. Anytime I do something like that, I'll wait a minute or two, then put my multimeter on it just to check and make sure that there's no voltage left across the output terminals. And if you're doing that, make sure you unplug it from the wall too. Just to be safe. It's always best to be safe.
And question.
Yeah.
On that LC circuit there, so that's filling in the gaps.
Right.
I mean, they're discharging when the voltage drops down.
Right.
To fill in the gaps.
Yeah. So let me draw that a little bit bigger, maybe. So if you just had a single capacitor there, right, what you'd see is kind of like voltage like this. Well, so as the voltage goes up, it keeps charging, and then when it starts going down, it goes down, but at a certain point, the capacitor will start providing some current, which will keep the voltage up. So you kind of see we're kind of getting to the point where we're getting closer to really a good DC voltage. Well, then if you put the inductor there, what the inductor does is it resists, it'll resist changes in current, and that'll help with the filtering. And then if you got another capacitor after that, it's even more. So eventually that ripple there, sometimes we call this voltage ripple. So that ripple will get smaller and smaller and smaller.
Good.
Any questions about that? Another way, another simpler kind of way I think about it is that, capacitors, the impedance the reactance goes down as the frequency goes up. So as if you got a certain frequency, AC at all, any kind of AC at all, that's going to shunt it to ground. It's another sort of way to think about it. And what you do is you optimize the L and C value to provide a high impedance to the 60 hertz or 120 hertz. I'm not a supply design expert, but I think you can see that, especially the capacitors, it'll once the voltage starts, it'll charge up to the maximum voltage. Then once it starts dropping, we'll resist that change in voltage by supplying some more current from, start discharging itself. So all this stuff I've been talking about are in power supplies called linear power supplies. And I don't know why we call it that exactly, but that's what we call it. There's another kind of supply out there you can buy called a switching supply. And the circuitry is much more complicated than this. And to be honest, I'm not sure I understand it fully, but it uses digital switching techniques instead of this, a big transformer and rectifier. Well, it's got rectifiers in them, but it's just a whole different type of circuitry. Because it uses the switching technique, it can use smaller transformers, and therefore there's lighter and smaller than a comparable linear supply. This 35 amp linear supply I have, is like about 8 inches by 8 inches by 8 inches. I mean, it's big. The 35 amp linear supply is like, easily half the volume and probably even less, and a lot lighter too as a result.
Hey, Dan?
Yeah.
One of the reasons they're going to the switching supplies is the switching supplies create a square wave instead of a sine wave.
Well, yeah, kind of. I mean, they're switching the AC, and instead of transforming the AC, and that allows them, like I say, to use smaller components and therefore be lighter, and actually they're more efficient too. But because they use this switching, especially in like say 10 or 15 years ago, the switching supplies were very noisy. I mean, they would generate a lot of noise that you could actually hear in your radio. Nowadays, they've improved the design so much that that's not quite so much a problem anymore. I mean, I would feel comfortable now about buying a switching supply, whereas I wouldn't have 10 years ago. In fact, that's why I've got the linear supply I do, because I just wanted to avoid any kind of switching power supply noise. But if I had to do it over again today, I probably would end up buying a switching supply. So that's the question. Which of the following is an advantage of a switch mode power supply as compared to a linear power supply? Answer: high frequency operation allows the use of smaller components. Any questions about power supplies? All right. Next session is about schematic symbols, and it references this schematic. And this schematic is of an oscillator circuit, an oscillator, maybe an amplifier too. You got two transistors there. And it just, the questions in this section just ask what symbols are, what are the numbered components? What do those schematic symbols represent? So question, and so there's no question about how this circuit operates. So you don't have to worry about that. You just have to be able to identify the schematic symbols. Question: which symbol in figure G7.1 represents a field effect transistor? Answer: component number 1. Field effect transistor. Which symbol in figure G7-1 represents a Zener diode? Answer: symbol 5. Question: which symbol in figure G7.1 represents an NPN junction transistor? Answer: symbol 2. Question: which symbol in figure G7.1 represents a solid core transformer? Symbol 6. And that's what these bars between the two coils are for. That's the solid core. Question: which symbol in figure G7.1 represents a tapped inductor? Answer symbol 7. I have a kind of funny story about Zener diodes. So one time, we're talking about this in class in college, and my professor says, yeah, I went to this conference, and I went to a dinner, and I was sat next to a guy named Zener, and we got to talking, and about half an hour into the conversation, I realized this is the guy that developed the Zener diode, but he pronounced his name Zener. So my professor didn't get it quite right off the bat. So we all had a good laugh about that. And that just shows too that, these things, haven't been around since time immemorial. It's like, well, it's been a while now since that happened, but even so, the guy was still alive, at the time. The Zener diode. So it really should be the Zener diode, not the Zener diode, but we all say Zener diode. Any questions about that? All right, let's take a 5-minute break because the next section I hate covering, and the longer I put it off, the more I like it. We're going to talk about digital logic next. So let's take a 5-minute break. Okay, so this is always the hardest, one of the hardest sections to teach because, like I said, in college, we took a whole semester of digital logic, and there's only a couple of questions on the test about digital, circuitry. So it's almost not, it's almost better to just tell you to memorize the answers rather than try and teach you anything about this. Although I hate to say it that way, but in digital digital logic, we have what are called gates, and gates perform a certain function. Okay. Two of the types of gates you need to know about on the general class test are the AND gate and the NOR gate. And it's usually an OR gate, but because the output has an inverter in it, built-in inverter, it's called the NOR gate. Okay, so what happens in an AND gate? Well, if this is A, this is B, and this is Q, we usually use Q for the output. This is the truth table for an AND gate. Okay, so the reason it's called an AND gate is both A and B have to be 1 for the output to be 1. And that's the question. Which of the following best describes the function of a 2-input AND gate? Answer, output is high only when both inputs are high. here's the truth table for an OR gate. Oops, I should have had 0, 1. Doesn't matter. So an OR gate would be, the output would be 1 if either A and B were 1, or both, either or both. But since we have a inverter, it's sort of the opposite. So the output will only be 1 when both inputs are 0. Well, wait a second. Which is 2 input? No, output is low when either or both input. Oh yeah, when either. Ah, that doesn't make sense. Oh yeah, it does. Sorry about that. See, I don't even get it right myself. Question, which of the following describes the function of a 2-input NOR gate? Output is low when either or both inputs are high. Wait a second. I was right the first time.
No, it's both.
I should have gone with my gut here. So, these aren't the only two types of things. There's NAND gates. There's like an AND gate with an inverter on it. There's exclusive OR gates. Oops. You know, so there's and then there's just plain old inverters, right? You get, and there's all these things, and they all do certain functions, and you can get them to do some very complicated logic functions. There's another type called the. Any questions about those two? I mean, that, like I say, it's almost best just to sort of memorize that answer. There's, oops. There's another type of circuit that's a little more complicated called the flip-flop. And this is a quote unquote 3-bit counter made with a flip-flop, with 3 flip-flops. What a flip-flop will do is it will change state when it gets a clock input. Okay, so if in whatever value is on D will appear at Q, and the inverse will appear at Q bar. So if D is 1 when there's a clock pulse, then this is 1 and this is 0. If D is 0 when there's a clock pulse, then this will be 0 and this will be 1. If you connect 3 flip-flops in this way, you'll count the number of clock pulses. Okay? And these outputs, A, B, and C, can have up to 8 different states. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and I'm running out of room here, but there's 8 different states. So question, how many states does a 3-bit binary counter have? Answer 8. In digital logic, we use the binary math system. So 3 bits will give you 8 states. Because 2 to the 3rd power is 8.
Dan, what are some of the practical uses for this system?
Well, in sort of nothing just off the top of your head, right? but say, actually, there's a little bit more use for what's the next question. Question: what is a shift register? Answer: a clocked array of circuits that passes data in steps along the array. So if you had, well, let me do this. What am I trying to do here? So if I had 3 flip-flops, just connected one to the next, and I had a serial data stream coming in here, and there was a clock signal, I could shift the data in. So if I had, like a serial port or a USB port, the S in USB stands for serial. So you get a serial data stream, and that would turn it into a parallel data stream. So that's sort of a practical application of it. If you see what I'm saying. So DQ, DQ, DQ. Well, actually, you take the here. So you see what I'm saying? So this data stream coming here, you clock it in, and it would turn this serial data stream into a parallel data stream. That's a practical use for it. And this is called a shift register.
Gotcha.
Because you're shifting the data. I know this is like quick and kind of vague in a way, but like I say, there's only 4 questions on the test about digital logic, and to go into a big long discussion of it. If you have a particular interest in this, I'm more than happy to talk more with you about it, and we can do that at some time, some other time. Nowadays, things are so integrated that we don't even really do this kind of thing anymore. We used to do lots of things with logic circuits. You'd have a big circuit here, and they have lots of inputs from you might have switches out here that controlled something, or some kind of sensor that gave you a digital output, and you put it into this digital circuit and you generate certain outputs. Well, now you don't do that. Why don't we do that? Because now we have little microcontrollers, Arduinos, for example, that are just as almost as cheap, right? You can buy an Arduino for $1 or $2, and not only is it cheap as like building your own digital logic circuit, it's programmable. So instead of changing the circuitry to implement whatever logic function you wanted, you just change the program. And in fact, that's what microprocessors were originally designed to do, to be logic circuit replacements. And doing it with an Arduino now is so cheap and easy. That's what we do instead of designing all these fancy circuits. So, that's why in a way, it's almost better to be a programmer than an electrical engineer now. And if you're an electrical engineer, you need to know something about programming, or else, you only have half the skills you need. I mean, even when I was doing engineering back, 30 years ago, I saw that need, and I did a lot of programming. I was a test engineer, and I wrote a lot of test programs. because that was the skill set you needed. Not, you didn't need to know all this. Well, you needed to know it too. You needed to know this hardware design, but you also needed to know the software design. Any questions about this? Again, I know it's kind of vague, and if you really want to delve more into it, I'd be happy to talk to you about it. But you know, there's only really 4 questions on the test, and I hate just blowing over it, but that's kind of the way it is. Oops. So let's talk about oscillators now. This is an example of an oscillator circuit. And yeah, you still might want to build this. I mean, there's certain needs for doing oscillator circuits. The question is, which of the following are basic components of a sine wave oscillator? Answer: a filter and an amplifier operating in a feedback loop. So that's what we have here. This transistor is basically an amplifier, but we're feeding back a portion of the output through this capacitor into this circuit here, which is called the tank circuit. And the L and C values determine what frequency is acting kind of like a filter, right? It's has a resonant frequency, and only letting a signal of that frequency get back into the amplifier. And that feedback loop is what produces an output at a specific frequency. And this is you can see this is a variable capacitor here. That's what that little bar means. So by varying the capacitance, you're varying the output frequency. And this works pretty well. I mean, I mean, you could, again, if you had some resistors and capacitors in one of these transistors, and the 2N3904 is like one of the most basic transistors you'll find out there, you could put together this circuit and make your own little oscillator. Question: what determines the frequency of an LC oscillator? Answer: the inductance and capacitance in the tank circuit. Because it's acting as a filter, it's only letting a certain frequency get through, which will then get amplified and fed back. So it's a feedback loop. Any questions about this? All right. So let's talk about amplifiers. There's different classes of amplifiers. And let me just, whoops. There's different classes of amplifiers, A, B, C, D. And really what these amount to is sort of the portion of the cycle, let's say if you had a sine wave input, over which the active component in an amplifier would be active. So A, it's 100% or 360 degrees. This is 180 degrees. This may be a little bit more than 180 degrees. And this is a lot more than 100, or a lot less than 180 degrees. Oh no, I take that back. This D. This is less than 180 degrees. This is the class D now is sort of like the switching power supplies. It uses switching techniques, and it's sort of not in the same ball game as this. Class A we use for linear amplifiers. And you may have heard that term. In amateur radio, we use linear amplifiers to amplify the output signals of our radios. And the thing about linear amplifiers is that it perfectly preserves the output waveform that you put into it, which is really what you want, right? If you're, especially if you're operating a voice mode, then you want to preserve that waveform, only make it a higher amplitude. So question, which of the following describes a linear amplifier? Answer, an amplifier in which the output preserves the input waveform. The problem with the Class A amplifier is that it's not as efficient as the B or C, okay? The C, it's sort of, in a way, counterintuitive. Since the active component is active for less than 180 degrees, you think, well, what good is that? Well, it actually is really good, and it's because it's more efficient. This is the most efficient of A, B, or C. And we can use this for FM transmitters because we don't care about the waveform so much. All we care about is the frequency. And this will preserve the frequency, if not the input waveform. So this is the type of amplifier we often use for FM. Question, which of these classes of amplifiers has the highest efficiency? Class C. Question, for which of the following modes is a Class C power stage appropriate for amplifying a modulated signal? Answer, FM. And it's also good for CW because, again, we're just sending out a carrier wave in CW. And then there's a question about amplifier efficiency. So if you've got an amplifier here, you're inputting some amount of power from your power supply, right? And you're getting some amount of output power. Well, the efficiency is simply the output power divided by the input, DC input power. And in most cases, you'll find that this is less than 50%. Okay, and so why is that important? Well, thinking about when you're going to buy a power supply, if you have a 100-watt radio capable of outputting 100 watts, and you're going to be using a 13.8 volt power supply, right? Well, you think, well, okay, I need about 7.5 amps, right? 7.5 times 13.8 gives you about 100. It gives you a little more than 100, but it's close, right? Well, that's at 100% efficiency. At 50% efficiency, you're going to need at least 15 amps. And chances are, for a 100-watt supply, you're going to need at least 20 amps because that's you know, it's not going to be 50% efficient. It's going to be more like maybe 35% or something. And you want to leave a little bit of margin there too. So that's why it's good to know about efficiency, because it makes a difference for the type of power supply the capacity of the power supply you buy. Any questions about that? And then there's finally a question here about linear amplifiers. A lot of times linear amplifiers use tubes. They actually still use vacuum tubes. And they can become prone to self-oscillation. The reason for that is, when we talked about the stray capacitance between the grids, the plate and the grid. Well, that can happen. So what you need to do is you need to prevent that from happening, you need to what's called neutralize the final amplifier stage. And what you do is you generally feed a little bit of the output back out of phase, which will then cancel out any capacitive feedback, which could cause the oscillation. That's called neutralizing. Question, what is the reason for neutralizing the final amplifier stage of a transmitter? Answer, to eliminate self-oscillations. So back when I got my general class license, it was tubes, right? I bought this thing called the Heathkit HW101. And even though it was not a really high power, it was, maybe like 150 watts input power. And in those days, we talked about input power, not output power, because that was the easiest thing to calculate, was the input power. But even then, you had to neutralize the final amplifier. And the way you did that was you stuck a piece of wire into there was a little metal cage where the final amplifier tube. You stuck this piece of wire in, and what that was doing was just acting as a capacitor, and you were feeding some of that output back into the input out of phase, and that's how you neutralize the final amplifier, that HW101. Fortunately, it wasn't too critical, because if it was real critical, then chances are I wouldn't have never been able to do it. But yeah, it worked. Any questions about amplifiers? You can build a little amplifier too. I did this myself not too long ago and gave a little sort of a little class on it at the library here, and that was fun. I had some 2N2222 transistors. I had a whole bag of them, and we all made amplifiers and got them working. And they were Class A amplifiers. Okay, let's talk about filters now. So we use filters a lot in ham radio. I mean, we have DSP filters, which do it all in software, but there's also hardware filters. And we talked a little bit before about how to use an op amp to create a filter. And so this section talks about different filter characteristics. So question, what is the frequency above which a low pass filter's output power is less than half the input power? Answer, the cutoff frequency. So here's a low pass filter, right? So it passes any signals whose frequency is less than the cutoff frequency. And this right here is the cutoff frequency. And you see it's half the amplitude of the highest value. And in fact, what is that point? That's the 3 dB point, right? Because 3 dB is half the value, the power ratio of 2. So that's the way we talk about bandwidth when we talk not only about filters but other things like you've heard of maybe the bandwidth of an oscilloscope. So if you have 100 megahertz oscilloscope, then when you're actually measuring a signal at 100 megahertz, that amplitude may be only half of the actual amplitude, because you're right at the edge of the bandwidth, or you're at the 3 dB point. So how would you use this? So if you were building a radio, you have an amplifier here maybe in your radio, and you put that through a low pass filter, and that low pass filter might have a cutoff frequency of say 50 megahertz, right? So you don't even though you're operating at HF frequencies here, your amplifier may generate spurious signals above whatever frequency band you're on. If you're on 20 meters, say you're at 14.3 megahertz, you could generate like a fourth harmonic would be at 57 megahertz. Well, if you pass the signal through a low pass filter, then you're going to filter out that 57 megahertz signal, and you're not going to radiate it. So that's how you'd use a low pass filter. One of the ways to use a low pass filter, and in fact, you probably want that cutoff frequency for for the 20 meter band to be lower. You probably want it to be like, I don't know, maybe 20 megahertz or something. But that gets to the next question. What should the impedance of a low pass filter as compared to the impedance of the transmission line into which it is inserted? Answer, about the same. So, if your radio has an output impedance of 50 ohms, you want the input impedance here to be 50 ohms. And then obviously you still want the 50 ohms output here. Why is that? Well, you want everything to match so you can transfer the most amount of power. So this doesn't, this eats up as little power as possible, or doesn't create, any kind of SWR mismatch, which would prevent the power from getting to the antenna. Question. Where is the bandwidth? Well, let's see. Oh, the bandwidth of a bandpass filter is measured between two frequencies? Answer, upper and lower half power. So here's the bandpass filter. If we just, that's supposed to be a straight line. But here's the lower half power point, and here's the upper half power point. So this right here is the bandwidth of that filter. Question, what term specifies a filter's maximum ability to reject signals outside its pass band? Answer, ultimate rejection. And that's like here. Like how far down will the signal be after it passes through the filter? How much will this band pass filter attenuate the signal? And then getting back to this, I should have mentioned it later, but so here you want this all to be matched, but even if everything's matched, even if you got 50 ohms here, 50 ohms here, 50 ohms, there'll still be some amount of insertion loss due to the resistances in there. You have the wire as a resistance. If you got coils, they'll have a certain resistance. They'll contribute some amount of insertion loss. And that'll be specified in dB, 2 dB maybe, probably less than that, probably more like 1 dB. But that's insertion loss, that's just a fact of life. You'll have some amount of insertion loss, even if your output impedance and input impedance are 50 ohms. Any questions about that? Okay. Let's talk a little about the transmitter. So this is a block diagram of a single sideband transmitter. Okay. Oops. Okay. So this is the oscillator that generates the frequency, you know, whatever frequency you're going to be operating at. Let's say 14.3 megahertz again. Here's your audio signal from the microphone. It goes into a balanced modulator. So if you recall, normal AM, right, you get the carrier plus two sidebands. Well, what the balance modulator does, it produces the two sidebands, but not the carrier. And I could describe how that works, but that really all you need to know is the balance modulator just produces the two sideband signals. So you got a double sideband going into the filter, this sideband filter. And this sideband filter will filter out one of these sidebands. On 14.3 megahertz, you want it to filter out the lower sideband. So at this point, all you have is the upper sideband signal. Put that through the linear amplifier and the power amplifier, and you got a stronger signal that then you send to the antenna. So that's the basic idea behind a sort of conventional single sideband transmitter. Again, you know, with software-defined radio, we do this a little differently nowadays, but these are the questions about the older analog kind of circuitry. So question, which circuit is used to combine signals from the carrier oscillator and speech amplifier, then send the result to the filter in some single sideband phone transmitters? Answer, balanced modulator. Question, which of the following is used to process signals from the balanced modulator, then send them to the mixer in some single sideband phone transmitters? Answer, filter. Because what happens sometimes, and I don't show it here, but sometimes this oscillator is sort of a local oscillator. It's always the same. And then after the sideband filter, they have another mixer stage, which then produces the actual output signal. I didn't show that here, but the balance modulator and the filter would still be the same. Any questions about that? All right. So this is the sort of the opposite of that. This is the receiver now. Signal comes in, it gets mixed. The signal comes in, gets mixed with what's called the local oscillator, and that produces an intermediate frequency signal. And in the simplest receivers, that's at like 455 kilohertz. That goes into the IF amplifier and detector. So all this operates at the same frequency range, around 455 kilohertz. They all operate at the intermediate frequency. Question, what circuit is used to process signals from the RF amplifier and local oscillator, then send the result to the IF filter in a super heterodyne receiver? Answer, mixer. And it says here, RF amplifier. Sometimes you have an RF amplifier stage. Usually you'd have an RF amplifier stage, I should say. Question, what circuit is used to combine signals from the IF amplifier and BFO to send the result to the AF amplifier in some single sideband receivers? Answer, the product detector. So this would be a product detector. Question, what is the simplest combination of stages that implement a superheterodyne receiver? Answer, HF oscillator, mixer, detector. So oscillator, mixer, detector. You could do without the IF amplifier, and yeah, you might be able to do without the AF amplifier. But you need those three circuits.
And I have a question.
Sure.
So you've got the RF coming in from the antenna, and that's some frequency, right?
Yeah.
And
Well,
you're
all
trying to-
frequencies.
well, all frequencies. So you're trying to get the modulated frequency or amplitude, whichever kind of circuit this is, and you're taking it and impressing it onto whatever's coming out of this VFO. So from that point forward, you're dealing with it with this 455 kilohertz. So if I understand this correctly, breaking this up into two different parts means that, you know, the front end could be AM, it could be FM, it could be whatever, but you only have to have this one single back end to process all those, I mean, or deal with those signals once you've got them out of the first stage.
Absolutely.
Okay, good, thanks.
Yeah, really, that's it. So all the frequency specific stuff is here, and everything after that is all 455 kilohertz. All right. So there's a random question in here about FM receivers, and really just this one question. So I didn't come up with any block diagrams for it. But question, what circuit is used in analog FM receivers to convert IF output signals to audio? Answer, discriminator. So instead of the product detector, you'd have what's called a discriminator. And, you know, so what's it doing? Well, here the product detector is actually demodulating the amplitude modulated signal. Here we're detecting the change in frequency, right? Because that's the difference between AM and FM. And so the circuits operate differently, so they're called a different value or a different name. So discriminator is for FM. Product detector for AM, single sideband, CW. Any questions? Okay, so let's talk about this oscillator for a bit now. So in the old days, we used actually, you know, LC oscillators, somewhat similar to what I showed you before, right? You had a bunch of capacitors and inductors, and you know, we switched different inductors in there to get different bands, and you know, that's what the band switch did. You know, the band switch would switch inductors and capacitors into that tank circuit, and then that oscillator would, you know, send whatever kind of frequency there. Well, now instead, those things were prone to failure, and I say that you know, just kind of seriously. You know, as you know, these things had tubes, and as the radio heated up inside, the L and C values would change, which means the oscillator would change, and you wouldn't be necessarily on the same, you know, the frequency would drift as the radio heated up. That's why you had to warm up your radio before you would use it sometimes, because you wanted the most frequency stability. After the temperature in the radio stabilized, then your L's and C's and the oscillators would stabilize. So nowadays we hardly ever use LC oscillators in like commercial radios anymore. Instead, we use what's called direct digital synthesizers, or actually any kind of digital synthesizer. But the question is about digital synthesizers. So direct digital synthesizers. And these are oscillators, so performs the exact same function, but because they're digital, they don't suffer from the same warm-up problems. And not only that, they're much more accurate than the LC oscillators were. So, and that's why we use them, because they're really right on. You digitally set the frequency of your radio now. Like I have, well, I had an IC 746 Pro that had a digital synthesizer in it. I set the dial to 7.030 megahertz, and by God, I was on 7.030 megahertz. And I would check it every once in a while against WWV to make sure I was on, dead nuts on. And these things were great. One time I was on the air, and I was talking to a guy, and he was using a Heath kit with an old LC oscillator in it, still using an LC oscillator. A third guy gets on the frequency. He says, "Hey guys," he says, I just fixed this radio. I'd like to get a frequency check." And so I'm sitting at a real nice radio. I said, "Yeah, you're on," I don't know, I forget what frequency it was. The third guy, the guy who was operating the Heath kit, he says, "Hey, I'm using a Heath kit. All I can tell is that you're in the 40-meter band." and that's kind of true. With a digital radio, you're plus or minus, hertz, or maybe 100 hertz. With those Heath kits, you were maybe plus or minus 5 kilohertz sometimes. It wasn't quite as bad as the band kind of thing, but it would drift. Things would drift and get out of calibration. But with these digital oscillators, you just don't have that problem. So they're really fantastic. I mean, really, they're just a joy to use, because you don't have to worry about drifting out of the band. You don't have to worry about your drifting into somebody else's contact. It's just stable and right on frequency. So question: which of the following is typical application for a direct digital synthesizer? Answer: a high stability variable frequency oscillator in a transceiver. Question: which of the following is an advantage of a direct digital synthesizer? Answer: variable frequency with the stability of a crystal oscillator. So, that old Hartley oscillator that uses the L and C, you could use a crystal there, and crystals do have good frequency stability. In fact, that's why when I first got a license, there was a class called the novice class license, and novices could only use crystal control transmitters, because the FCC didn't want to worry about novice class licensees not being able to control the stability of their transmitters. So they required them to use crystal control transmitters. Any questions about digital synthesizers? All the new radios you buy today will have these things. And like I say, it's just fantastic. All right. So here's the last topic: software-defined radio. So nowadays, it's not even just good enough to be digitally controlled and digital oscillators. We do everything digitally now almost. And this is a block diagram of a software-defined receiver. And what happens is, the signal comes. Whoops, signal comes in, maybe goes through an amp, maybe goes through a filter, sometimes not even then. But then the signal sort of gets shifted into two 90 degrees out of phase signals, if you will. And they're called the I and the Q signals. And then these are converted into digital, so at this point, there's still two analog signals 90 degrees out of phase with one another. Then they're converted to digital, and then they're fed right into a digital signal processor. And all the magic happens right here. The bandpass filtering, the demodulation, all that stuff happens here. Then it'll output like an audio digital stream, which then goes to D to A, and then through that, and then you actually get audio out. But all the magic happens in the digital signal processor. So question, what is meant by the term software-defined radio? Answer, a radio in which most major signal processing functions are performed by software. Question, what is the phase difference between the I and Q signals that software-defined radio equipment uses for modulation and demodulation? Answer, 90 degrees. Question, what is an advantage of using I and Q signals in software-defined radios? Answer, all types of modulation can be created with appropriate processing. So the reverse also works. What they're talking about in this final question is sort of the reverse. You can generate the I and Q signals, feed it into a digital signal processor, which will then generate an output signal that would be connected, instead of to a speaker, to an antenna, in the transmitter case. But you can do, so what you can do for receive, you can also do in reverse.
Question, Dan.
Yep.
So in that digital signal processor there, is that software like set in there, or is this software that can be changed or loaded? I mean, what is that thing?
Well, good question. So the answer is yes and no. If you bought an IC 7300, it's got a digital signal processor in there, and you can't do anything with that, okay? On the other hand, if you bought an IC 7610, you could get the I and Q signals out of it, and then you could feed that into your computer, and you could do whatever you want with those I and Q signals. You can set you can load some signal processing software yourself, develop some special modules, and decode it yourself. In fact, this is another one of the things I keep threatening to do, which I haven't done yet. There's a thing called GNU Radio. So it's open source software for doing digital signal processing. And you can download it and design your own software-defined radio if you want. All you got to be able, then all the hardware you need is this hardware to be able to feed the I and Q signals in. Or have a radio that has IQ outputs.
Interesting.
Yeah, I mean, it's fascinating, actually. It's fascinating. They just had this GNU radio. Every year they have a conference for users of GNU radio. And they just had the conference. And it was all online. And I'm sure the recordings are now online if you want to look it up and watch some of them. I just didn't get around to it, because again, this is one of the things. There's so much to learn. It's like incredible. And, this is just one of them. The other thing I've been doing lately is trying to learn how to operate the satellites. Well, that takes time. Another thing I've always wanted to do, which we'll talk about a little bit later, is learn how to model antennas. Right? There's software that you can put in the parameters, and it'll give you like feed point impedances and radiation patterns and all that. I keep threatening to learn how to do that, and this is all free software. This GNU Radio is open source software. There's free antenna modeling software that you just download and play with. There's just too much. There's too much to do. All right. Any questions? Any other questions?
I have a question.
Sure.
So So these guys that came up with this FT8,
Yeah.
so were they working with, I mean, is there signal processing happening in this, or is that somewhere else down the stream from this?
Well, okay, so that's a good question too. So what's happening with FT8 is sort of, they probably, you take the signal out of the radio like about right here and feed that into your PC, running the WSJT software. And then whatever WSJT does with that audio signal is, it's done inside the WSJT software but the radio itself, whether you got an IC 7300 or whatever, it's still doing the digital signal processing thing here. And actually, I take that back. So you could be doing it this way, could be doing the audio, but like if you had an IC 7300, oops, what happened? You'd be using the USB port and you'd be feeding digitized audio. It's still audio, but it's digitized audio. So the computer doesn't have to re-digitize it. But you're still feeding I and Q signals in.
Yeah, I see that. This is further processing downline, but the fellow was talking about this today was talking about, use a sound card basically if you're coming off of that codec
right
there.
Here
But if
you'd be using the sound card.
And if you have a modern transceiver, then you'd be coming off the USB port.
Right. So when I had the IC 746 Pro, I did the sound card thing. When I got the IC 7300, I went with the USB port.
Very interesting.
Yeah, it's fascinating stuff. It's really fascinating stuff. All right. There's no other questions. I hope you all have a good weekend.
Dan, what should we study for next class?
Oh, good question. So next week, we are going to talk about signals and emissions.
Thank you.
Yep.
Hey, Dan, just an FYI, Lark is doing a Lark in the Park on Saturday at 11:30